Hey, IBAASL2. Remember that we have a second opportunity on optimization coming up. So I'm going to do a couple more videos, starting with this one about optimization. And then eventually I'm going to show you guys kind of some tricks on a graphing calculator so you can check to see if your answers are right. First example, the cost to produce X items in euros is that function right there. Find the number of items to minimize the cost. Justify your answer. This is a pretty straight up optimization problem. Like, you don't even have to set up the equation. It's given to you right here. And it's not like a profit one where you have to subtract out the cost from the revenue or something like that. So this one you can just straight up take the derivative. And then we have to figure out when that's at a minimum and justify our answer. Remember that minimums and maximums happen when at the turning points, when the derivative is equal to 0. All of these things are divisible by 3. So we get x squared minus 2x minus 3. So then factor the right-hand side, and we get x minus 3, x plus 1. So when you set them both equal to 0, we get 3 and negative 1. But then the question is, which of these is a maximum, which is a minimum? So, or maybe they're both maxes and both minimums. I don't really know. You could do this with a zone test, but if we're just going to check to see if they're maximums or minimums, I prefer to use the second derivative, which is going to be 6x minus 6. When you plug a 3 into 6x minus 6, you get 18, take away 6, which is 12, which is a positive number. Remember, a positive number means that the graph is concave up in that zone, which means that that is a minimum. So when the second derivative is positive, that's the minimum. So when they make 3 items, the cost will be at a minimum. Next problem, a very classic optimization problem. A rectangle is inscribed underneath a curve, and the curve is given by this equation right here, 2 cosine 1/2 x. This is only going between negative pi and pi, so I assume that that's, this on the picture is negative pi, and this is pi. That doesn't really matter, but yeah, we'll get into it. So the rectangle is inscribed into the curve. A and B are on the x-axis, and C and D are on the curve. The coordinates of B are x0. So that makes sense. If you think of this distance right here as a distance of x, then this coordinate is x comma 0. The second part of that says the coordinates of C are x comma 2 cosine 1/2 x. So you might look at that and go, what on earth are they talking about? But they're talking about the coordinates of this right here. Obviously it goes x over to the right because this is the same distance as x. But then this distance is essentially the same distance as the y value of the coordinate. So how do you find y values of coordinates? Well, if you have an x value, you plug them into the function. The function is right here. So if you want to know the y value when you go x to the right, how far it goes up on the curve, the output is the answer. So that's 2 cosine 1/2 x. So that coordinate is 2 cosine 1/2 x tall. That also means that that is the side of this rectangle. The side of the rectangle is 2 cosine 1/2 x. Now, part A says write down the expressions for the lengths of AB and BC. Well, if I look at AB, that's this total distance right here. So if this is x on this side, there's another x distance that's the same on this side. So this is another x distance. So that entire side is going to be 2x. So AB is equal to 2x. and the length of BC. Well, I kind of already talked about it, that this length of BC right here is just the y value of the c coordinate. So that is 2 cosine 1/2 x. So BC equals 2 cosine 1/2 x. Next up, it says write an expression for the area of the rectangle ABCD in terms of x. So let's call it a of x. Well, the area of a rectangle is just length times width. So ax, the length was 2x, and the width was 2 cosine 1/2 x. Which we can clean up and call 4x cosine 1/2 x. So that's the area equation of the rectangle. Next up, find the derivative of that. When I look at this, I see, gosh, it's 2 rules. It's going to be a product because it's something times something, but then it's going to be a chain in the second part of it. So it's a product with a chain inside of it. First, d second. Now, d second is going to be negative sign, but then it's a chain rule where you have to take the derivative of the outside, keeping the inside the same, times the derivative of the inside. So that was first d second. Then we have to add second d first. So second is 2 cosine 1/2 x times the derivative of the first part. Second d first. Yeah, okay. That's 2. Let's do just some minor cleanup here. This 1/2 multiplied with the 4 gives you 2. So we get, and I should bring that negative out front. So we get negative 2x sine 1/2 x. And then the 2 2's back there give us 4 cosine 1/2 x. Now we need to figure out when the area is at a maximum. So what we're going to do, obviously, is, not obviously, but anytime you're finding a max or a min, is set the derivative equal to 0. So we get negative 2x sine 1/2 x plus 4 cosine 1/2 x. So for this part, if you try to solve this by factoring and things like that, you guys don't really have the tools to be able to do this. So this is a situation where you'd have to use a graphing calculator. So what we're going to do is put this into y1 in our calculator. When you do that, you should see a graph that looks something like this. Oh, and you're setting your window from negative pi to pi, because that's what it was restricted as on the original problem. So when you graph this, from negative pi to pi, it looks sort of like a parabola. It's not really a parabola, it's like a weird trigonometric, but it looks something like this. Then, to find this point right here, you can use the maximum feature on your calculator. And I'll try to post a better video about how to actually use the calculator and the calculator steps. But if you are looking at a graph, and then if you go to second calc, okay, so I'll write out some of these steps for you guys. So, to find max, you go second calc. Well, I'm sorry, second trace button. It's the button up at the top. It's sort of in the middle to the right. So second trace, which is the calc button. And then in that menu, you're going to find number 4, which is maximum. Then if you hit maximum, you're going to get 3 prompts. The first one is, second calc. Left bound. So the left bound, you have to pick a place, like use the arrow keys to pick a place that's to the left of the curve. So if I'm looking at my graph over here, like you've got to put your left bound somewhere over here. So left bound has to be somewhere to the left of the maximum you're looking for. So left bound somewhere on left. Then once you do that, it's going to ask you for a right bound. So using your arrow keys, shift it over to somewhere on the right and then hit enter. So, the left bound's on the left of the maximum and the right bound's on the right of the maximum. Then, this is kind of a funny one, but it's going to say guess. When you do guess, you just want to put it somewhere near the top. It doesn't have to be exact. In fact, I kind of prefer it not to be exactly on it, just slightly to the right or the left, because when you line it up there, that's not the actual maximum. You have to hit enter again, and then it's going to tell you the max. So what happens is that the left and right bound, the calculator starts looking only in between the left and right bound, and then it's going to tell you what the y value, the actual coordinate is of the highest point in between, which will be this one. When you do that, you get 1.72. So here, solving this, you get x is equal to 1.72. Yeah. If you plug that into the second derivative, which taking the second derivative is hard, it will verify it's a maximum, but we kind of already knew it was a maximum from graphing the derivative. I would recommend graphing the OG function. So go back up to this guy right here, punch this into your graphing calculator, and then you'll see a graph that looks like this. Only between negative pi and pi. Then if you use that same maximum feature to put a left bound, right bound on these guys, and then find whatever this is up at the top, this is going to have an x value of 1.72. So there are problems like that rectangle inscribed in something where you can do it and the algebra is actually doable, that you don't have to resort to a graphing calculator. But in this case, we did have to. Certainly when it comes to test time, we'll let you know, how it's going to work in terms of what needs a graphing calculator and what doesn't. All right, you guys.